We are now going to move on to talking about pulse code modulation and quantization. This is the bridge from analog to digital modulation. All right, so this is the basically it's the details of the analog to digital conversion. All right, so pulse code modulation is the method that's typically used to digitally represent sampled analog signals. All right, so here's a typical workflow for a PCM generator. Point one, we start off with the message MFT. The assumption is that the bandwidth of MFT is W. Okay, so this is my baseband signal, my sort of raw unprocessed signal, the thing that I want to digitize and transmit. Now, the first thing that we're going to do is the first thing in the digitization process is we're going to sample in time. Right? So block 2 is a sampling block. It discretizes in time, and when you sample, you need to have a sampling frequency. We're going to assume the sampling frequency is 2W. Okay? Can you guys guess why the sampling frequency is 2W? Could I have it be less? So the answer is actually, you could have the sampling frequency be whatever you want, but your performance will suffer. If the sampling frequency is below 2W, you will get aliasing, right? Meaning that you will not be able to reconstruct the signal at the receiver. So the minimum sampling frequency is the Nyquist frequency, which is given by 2W. So let's assume that, because we want to sort of just operate with minimum requirements right now. So sampling is fine. This is what's covered in EE2023. Now, the next step is block 3, which is quantization. Now, quantization is probably something you have not done, but the point of quantization is to bin into quantized values, right? So you're going to take these continuous values here. So this is at the output of block 2, things are sampled in time, but they're still continuous in value. So this bins into quantized value. So this is what we're going to talk about in this section of the class. And then finally, there's output of the quantization. You get bits, and you want to take those bits. You don't transmit bits. You transmit waveforms. So we need to take those bits and convert them into sequence of pulses, and that's going to be the PCM waveform. Okay. So what we're going to do in this lecture is we're going to talk about quantization, and we'll talk a little bit about the PCM waveform. Okay, so here's an example of a midpoint quantizer. Okay, so remember that quantization is a process of mapping input values to a smaller set of, to a smaller discrete set of output values, right? So if this solid line here is my signal to be quantized, right? This is my, I'm gonna put time on this axis, value on this axis. So this black curve is the signal to be quantized. You can see it's continuous over time. So the first thing we do is sample it. So these tick marks here are the sampling points, right? So this is, for example, so if this is 1, 2, 3, 4, 5, this is sampling 0.5, or if I'm sampling every second, it's time t equals 5. And this x is the value of the signal at time t equals 5. Okay. Now to build a quantizer, I need to define a set of discrete output values. So in this case, what I've done is I'm gonna take my range here, convert it into bins. So for example, 0 to 1 is a bin, 1 to 2 is a bin, 2 to 3 is a bin. And any signal that falls in this range, let's say between 1 and 2, will be represented by some value, which is the quantized value. And in this example, I'm showing you a midpoint quantizer. So the quantized value is the midpoint of the bin. Okay, so these dotted lines here are the quantization levels. Okay, so if I take time t equals 5, the actual value is represented by this x here, and it's about 5.2, but it's in the bin between 5 and 6, and the quantized value for that bin is 5.5. So I'm going to replace 5.2 by 5.5. So the quantized value is 5.5, right? Now, I told you that we're going to eventually have to generate bits. So what now in this example here, I have 1, 2, 3, 4, 5, 6, 7, maybe 8 bins, 8 levels. And so if it's 8 levels, to differentiate 8 things, I need 3 bits. So I'm going to give each level, I'm going to map it to a sequence of 3 bits. So for example, maybe this level is 0, 0, 0, this level is 0, 0, 1, and so on. So we see that level 5 here was 1, 0, 1. So the transmit value for t equals 5, which was the actual value was 5.2, the quantized value was 5.5, the bit representation of that is 101. So I'm going to transmit 101. Okay, and when we look at PCM, we'll see that 101 will correspond to a certain sequence of binary pulses. Right, so this is like, it's important that you understand what's going on here, because this pretty much tells you everything about quantization. It doesn't give you the analysis, which we're going to do next, but it kind of explains the idea behind quantization. So this is essentially an analog to digital converter, right? You sample in time, you quantize in value. You go from analog values to bits. So again, remember, quantization is the process of mapping continuous input values, or possibly continuous input values, to a smaller discrete set of output values. All right, so let's move on then. Okay, let's look at the bandwidth requirements of PCM. So we saw over here that there are quantization levels. So let's assume that the number of quantization levels is Q. So I'm going to introduce some notation, and we'll try to be very consistent with the notation, okay? So Q, otherwise, if you're not, if we don't redefine it, will be the number of quantization levels. And in this part of the notes here, N will always be the number of bits per sample. So here, because there were 8 levels, the number of bits per sample was 3. So N is the number of bits per sample. So of course you see the relationship between number of levels and number of bits. So if you have N bits per sample, you'll have 2 to the N quantization level. Now, if it turns out that Q is not a power of 2, that's also okay, right? But you can't get away from the fact that you need at least 2 to the N bits to represent Q level. So as usual, we let M of t have bandwidth W. The sampling rate will be 2W, and it might be useful to look at the sampling interval. So sampling interval is just 1 over Fs. So Fs is just 1 over the sampling interval. So now we are generating samples at 2W samples per second. That's what sampling rate means, right? And there are N bits per sample, and each bit is represented by a pulse. So the pulse transmission rate is 2W times N pulses per second, okay? So when you do this process here, at 0.5, you're generating 2WN pulses per second. And the bandwidth of that signal would depend on the shape and characteristics of the pulse. So if the pulse is a square wave like this, right, and if I have 2WN pulses per second, each pulse can be at most with 1 over 2WN, right? Because there's 2WN of them in 1 second. So now the bandwidth of a square pulse or a rectangular pulse is sync. We know that the sync has its first zero crossing at at 1 over tau, right? So now again, the sync has infinite support, but we need to get the concept of effective bandwidth again. And in this case, I'm going to just use the first zero crossing. If the first zero crossing is at 1 over tau, the bandwidth is 2WN. And because there's some approximation going on, I put a K here as a little fudge factor. Okay, but the bandwidth scales as 2WN, and we know N is log base 2 of Q from here. So in terms of Q, the bandwidth of a PCM signal is this 2kW log base 2 of Q. Okay, and this is the minimum bandwidth that's required for a PCM signal. If you have less bandwidth, you cannot transmit this PCM signal. Okay, I'll just point out that this is actually quite bad. The sync is a very bad function because I made the approximation that the first zero crossing is the bandwidth, but it turns out there's a lot of energy outside the first zero crossing. So practical systems don't use rectangular pulses which have sinks as Fourier transform. Practical systems do pulse shaping, and the pulse shaping basically reduces the bandwidth requirements. The most popular pulse shape to use is what's called the root raised cosine pulse. Okay, and the root raised cosine pulse has very nice frequency properties, meaning its first zero crossing contains a lot of the energy. Like practically all of the energy is in the first zero crossing. Okay, so, and here's a link to Wikipedia that talks about the root raised cosine filter. Okay, but I don't expect you to memorize the root raised cosine, but I expect you to understand why the rectangular pulse is not ideal and why we need to do pulse shaping. And basically, this is the pulse shape that's used. Okay, so let's go on. So remember, what are we doing? We are replacing, I'm replacing 5.2 by 5.5. So you can see there's an error, right? So we're going to call that quantization error. We're going to treat it as noise. Okay, so on slide 3 here, I'm saying that quantization is a process of mapping the input to some value, some output value, right? Okay, so X is the input value. XQ is the quantized value, right? Delta is the size of the bin, the quantization interval. And for the midpoint quantizer, if X falls in the ith interval, I replace X by XQ. Okay, and XQ is the midpoint of the ith interval. And the midpoint of the ith interval is just Xi minus 1 plus Xi divided by 2, right here, right? Delta, which is the quantization interval. Now, I'm going to assume uniform quantizers. Uniform quantizer means all the bin sizes are the same. If all the bin sizes are the same, if I have Q levels and a dynamic range of B minus A, suppose the signal has max value of B and min value of A, so the dynamic range is B minus A, right? If I have Q levels and the bin size, if I have a uniform quantizer, is B minus A over Q. We want to be on the same page in terms of notation, right? We know what the value is. X would be the input value, the original value. XQ is the quantized value. For a midpoint quantizer, XQ is the midpoint of the interval. Then once you have this, you can define the quantization level boundaries. All right, so page 3 is just sort of notation to set things up. If you get confused about notation, just come back here. Okay, so as I said, we're going to replace X by XQ, and that causes an error. Right, so I'm on slide 4 now. We're going to replace X by XQ. That causes an error, and the error is X minus XQ, and we're going to essentially treat this as noise. XQ equals X plus error, right? So it's like I receive XQ, the error that's added is X minus XQ, right? So it's in some sense just like additive noise. What we're going to do is we're going to model our signal X as a random quantity, as a random variable with probability density function, PDF, of fx of x. And once we do that, we can compute the average quantization error. Okay, and this average quantization error will be my metric to represent how much noise I'm adding, right? And if so, expected value of X minus XQ, so this is the error. So the expected value of the error squared is just the integral over the support, which, you know, X goes from A to B. The only thing random here, by the way, is X. So this expected value is over X. Okay, so and X is defined from A to B. This is the value I want to average, and this is the PDF of X. Right, so this is sort of just standard application of definition of expected value, and then I'm going to just plug in. So if you go back here, remember we define all this notation here. I just plug all that in. X minus XQ is just this. Fx of x is this. Now since the integral is a linear operation, the integral from A to B is the same as the integral over all the bins. Right, so that's what this says. This is the integral from one. This is the integral over one bin. This is the summation over the Q bins, or the Q levels. Okay, and depending on what fx of x is, you can evaluate this integral, and we'll call this thing NQ. As I said, this will be the measure of how much noise I'm adding. So it's effectively the noise power at the output of the quantizer. It characterizes how much noise quantization is adding. Okay, now you can probably see where we're heading. If we're going to characterize the noise power, let's also characterize the signal power. Like, and signal power is just my signal that I'm transmitting is XQ. So the signal power is just expected value of XQ squared. So again, just applying the definition of expected value. it's expected value over X still, so it's this. But this, once you plug in what these things are, you get this equation here. And again, when you get what fx of x is, you can evaluate this. Okay? And then when you take the ratio of these two, we call this the signal to noise ratio at the output of the quantizer. And this measure here, this signal to noise ratio, sometimes it's called signal to quantization noise ratio, because remember, in a communication system, there's other sources of noise, meaning the channel. Okay? But in this context, we are not really talking about the channel. We're talking about the noise added by the quantization process. And so this signal to noise ratio at the output of the quantizer measures how good the quantizer is. So of course, the higher the signal to noise ratio is, the better the quantizer is. The lower this signal to noise ratio is, the worse the quantizer is. Okay, and so often what we do, and I wrote it as a function of Q, I wrote SQ and NQ because that's what the system designer can tweak. You can control the number of levels, right? You can have a 1-bit quantizer, a 2-bit quantizer, a 3-bit quantizer, a 16-bit quantizer. And what you'll normally find as you increase Q, the signal to noise ratio increases. Okay, it's not surprising. As you increase the number of levels, if you go back to this picture here, the more levels I have, the better approximation the quantized values are. So we got to this point. Let's end. We'll end. I'll just go through an example here, okay? So this is an example. Now, remember, we are modeling X as a random quantity, so I need a distribution for X. This fx of X. In my example, I need to choose a PDF for X. So I'm going to assume that X has a uniform distribution on minus A to A. Okay, so the dynamic range is minus A to A, and I'm going to assume that X is uniformly distributed. So that means fx of X is 1 over 2A, right? Because the range is 2A, you know that 2A, and the uniform means that it's constant, and you know that when you integrate fx of X, it has to integrate to 1, right? So the only choice you have is that fx of X is 1 over 2A. 1 over 2A times 2A equals 1. All right? So this is what my sort of diagram looks like. My signal goes from minus A to A. I'm going to assume, again, let's assume a midpoint quantizer. So I'm going to have these levels. The midpoint of the level is going to be my quantized value. Remember the level boundaries, again, that was here. The quantization level boundaries are just, from lower level plus I times my bin size. So in this case, my level boundaries are just A plus I delta, and I want the midpoint. This thing is of size delta, so I have to add or subtract delta over 2 to get this midpoint here. So my quantized value is given here. So I'm going to write this as a function of delta here, okay? Later we'll connect delta back to number of levels, okay? So NQ is just, so this is the noise power, is summation over all the levels, the integral over one level of the error squared, and fx of X is 1 over 2A, so 1 over 2A, right? And mi was given by this quantity here. You substitute that in, do some algebra, and you get this. In this example, we see that like if I have Q levels and the dynamic range is 2A, delta is just 2A over Q, right? Remember, we did that here, right? Delta was just the dynamic range divided by the number of levels. So delta is 2A over Q, so Q delta is 2A, and I use that here, okay? Where once you work that out, you will get that NQ is just delta squared over 12. Okay, SQ is kind of easy to compute because it's just mi squared. Yeah, so fx of X is 1 over 2A. The xq squared is just this squared, which will turn out to be mi squared delta. And you work that out, you will get that SQ is just this quantity here. And then you take the ratio. So the ratio of this to this, it's q squared minus 1. If q is large enough, this is approximately q squared. And this is in ratio mode. If I want to convert to dB, it's 20 log Q, right? So this is my signal to noise ratio represented as a function of Q. So let's see, again, for a uniform quantizer, for a uniform distribution. So there's two uniforms here. Please don't confuse them. I have a uniform distribution for the input, and I have a uniform quantizer, right? Uniform quantizer was here, right? That all the bin sizes are the same, okay? And uniform distribution is an assumption on the input source. So for a uniform source with a uniform a quantizer, the signal to noise ratio has a very nice form. This is 20 log Q. What this means, so let's see like what kind of insights we can derive from this. What this tells you is that if you add 1 bit to the quantizer, right, it gives you a 6 dB gain in the signal to noise ratio. Adding 1 bit to Q does what? If I add 1 bit, if instead of an n bit quantizer, I have an n plus 1 bit quantizer, what happens to the number of levels? The number of levels is 2 to the n. If I go from n to n plus 1, I'm going to double that, right? 2 to the n and 2 to the n plus 1. 2 to the n, if you double it, you get 2 to the n plus 1, right? So the number of levels double, so this becomes Q squared. Log of Q squared is just 2 log Q. So the signal to noise ratio doubles. If the signal to noise ratio doubles, that's essentially because of this 20 here, you essentially get a 6 dB gain. Okay, so there's a 6 dB increase in the signal to noise ratio for every bit that you add to the quantizer when you have a uniform source using a uniform quantizer. The second point I want to make is that for a uniform quantizer, all quantization regions are of equal size, right? And this is good for uniformly distributed inputs. We get really nice results like this, right? Like that adding 1 bit gives you 6 dB gain. You can also show all sorts of optimality things, that a uniform quantizer is essentially optimal for a uniform source, okay? So this is good when your source is uniformly distributed, okay? When the input source has a uniform distribution. What happens if the input is not uniformly distributed? Because not all, not all sources are uniformly distributed, like your MP3 file or even a sinusoid is not uniformly distributed, right? And certainly your MP3 file where some people are playing guitar, piano, mixture of all sorts of instruments is clearly not uniformly distributed. So the question will be, what do we do in that situation? And we'll pick that up when we come back. Okay, thank you very much.